Hello, dear fellows. My name is Hsieh. Today I represent Tensor Tech to give you this presentation about the topic, a novel attitude control system minimization solution using reaction sphere. So let's get into the topic. So every satellite in space, they need to control its orientation along X, Y, and Z axis. So the technique that helps each satellite to do so is called attitude control. However, the traditional way people control the satellite is like the picture shown in the left-hand side. There are at least 3 motors we call reaction wheels, and there are 3 magnet torquers that are actually copper coils applied with currents. So the traditional way people design this attitude control system is by aligning each of the reaction wheels in the x-axis, y-axis, and the z-axis. And together, they also need the copper coils to provide a magnetic moment to interact with the Earth's magnetic fields to produce the torque that is necessary for the desaturation for those reaction wheels motors, while those motors are reaching to its maximum speed and can no longer accelerate anymore. And back to 3 or 4 years ago, when my team and I worked for the National Space Organization for my country, Taiwan, and then that's the first time that I get into the domain that is designing for the single axis motor for the National Space Organization in my country. Back then, we found that every satellite, they took nearly 30% of the weight or the volume for the attitude control system, just for these devices. However, we found that by decades, that the evolution of satellite hardwares, such as the onboard computer, the electrical power system, and these keep shrinking in sizes by time. However, the attitude control system that remains nearly the same size from maybe 20 years ago to now. So we believe there's something we can do to help the satellite to get even more smaller. So this is why we proposed the spherical motor technology back to 4 years ago. And then we designed this motor that was a reaction sphere. And this reaction sphere has a spherical rotor which can spinning in multiple axes. So we control the orientation of this rotor by manipulating the magnetic field inside of the motor, and then to use this rotor to exchanging angular momentums in multiple axes. So at the end, we are capable of providing nearly the same performance with the traditional attitude control systems with nearly 1/3 of the weight, volume, and power consumption. Okay, so let's look at how it works. You can see from the video that this is the showcase of our device. And there are a spherical rotor continuously rotating inside of this cylindrical box. And plus, there are also the circuitry boards surrounded by this reaction sphere. And then these provide the control circuitry and also the driving circuits. So this is combining them all. This is called our RS100 products, which stands for the reaction sphere that is capable of providing angular momentum storage capacity up to 10 millinewton meter seconds. And plus to save the trouble from our customers, we also provide an attitude control system, which is an integrated solution. And then this solution is combining the fine sun sensors, magnetometers, and gyroscope, as well as the most importantly, the attitude control algorithms in. So our customer are able to just input with the attitude command and without thinking how to build the algorithm inside of this complicated integrated NECS system. Okay, so and this device is going to be launched in space this year in June. That's with a European satellite and launched by SpaceX rocket this year. And this will help us to gain the first flight heritage. We hope in the future, perhaps we can have some cooperation with your satellites in the future. And so let's get into the technology details of this reaction sphere. So this is the mechanical structure inside of the rotor. If you cut it in half, you can see there are the rotors arranged in the 2 degrees of freedom style. And there are hexahedron stators outside for collecting the magnetic flux linkage exerted from this rotor equipped with magnets. So these magnets are actually arranged in the 3 poles design. And so while the rotor is spinning continuously, the rotor, the stator will collect the magnetic flux linkage in 3 times of the frequency over its rotational frequency. Okay, so the second thing that you will probably be interested is the design of this rotor. Its mechanical degree of freedom is actually only 2 degrees of freedom. So in terms of the rotational dynamics, it is actually a variable speed, single gimbal control moment gyro. So let's take a detailed look at how it works in the motor side. So let's look at the scenario in the upper left-hand side of the diagram. You can see when the copper coils are arranged in a hexahedron style, then we connect the opposite side of the coils as one phase. So there are phase A, phase B, and the phase C. They are arranged just like a box to be able to collect the most of the flux that is exerted by the rotor. So the scenario 1 is that when tilting angles go to 0, then the rotor's magnetic poles are aligned into phase A and phase B. So only phase A and phase B are collecting with magnetic flux linkages. And while the tilting angle are getting larger, like for example, the 15 degrees here, or the 30 degrees here, or even 45 degrees here, you can see that the magnetic flux linkage, or you can see here is the induced voltage, are getting varying with the linear projection relationship. You could simply calculate it by the sine cosine relationship. You can see that's how we control the orientation of this reaction sphere within its tilting axis and then the rotational axis by applying the correct current in phase with the induced voltage. So we can generate the maximum mechanical power, and then by dividing it with the mechanical speed, we obtain with the torque. That's basically the principle behind the motor side. And the second thing here is the torque exerting mechanism. You can see from this picture, this is the motor. If we specify the frame in the gimbal, so there are gimbal frames x-axis, gimbal frames y-axis, and gimbal frames z-axis. So in terms of its x-axis, the torque exerted by it is actually the so-called gyroscopic torque. That's it could be one of the most powerful axis this motor can exert its torque to apply on the spacecraft. And then there are the second axis called the y-axis, which has the same characteristics with the reaction wheels. That is, its torque is simply obtained by the acceleration and the deceleration of the inner rotor speed. And there are the z-axis torque, which is fairly small because omega z is usually very small. So and the only time we will have omega z is when the tilting axis is making some actions. So then there will have a z-axis torque. However, we usually treat z-axis torque as a noise, and we will often get it rid of by the control on our magnet torquers, because the z-axis torque is too small for us to get the best use of it. And if we want to use it, then the control will be very complicated. So that's why we use the magnet torquer to control the z-axis of the satellite, and which the moment of inertia in z-axis is usually smaller than the rest of the axis. So that's why we put the z-axis aligned to the smallest moment of inertia axis of the satellite. So this is a torque exerting mechanism. But for users, you don't have to worry about how to manipulate with those complicated design factors. We have already embedded those calculation algorithm into our RS100 product. So you only have to input with a torque command. Or if you purchase our ADCS 100 product, then you simply input with the attitude command that you desire. And then our product will automatically rotate to the desired orientation for you. Okay, so then there are some pros and cons for you to make comparison. And obviously, the first thing is the lower weight, power consumption, and volume for this motor. And the z-axis torque is indeed another important issue that we have to deal with, because it can only be exerted by the magnet torquer. And also the third thing is about the torque output accuracy on YZ axis, because it is largely depends on the tilting angles control accuracy. And by experiences, we know that for motor control, that in the X and Y axis is much more difficult than the speed control. And so this puts some difficulty for us to design this motor. However, we're getting rid of some optimization on sensors, algorithms, and filters, such on. And the last thing is the benefit of this motor is that since it utilizes the gyroscopic torque, so it can achieve high torque versus power consumption ratio. However, this benefit is only significant on the larger spacecraft. If the spacecraft getting larger, then this benefit getting more and more important. The relevant references you could find from the Dawson Clear's publication a few years ago. So there are some references for you to look on. So we are Tensor Tech, and we dedicate on the minimization of satellites. And we hope by adopting our technology that people are able to shrink their satellite more smaller, and then to make more value from the emissions, and then save the cost for them, so that this industry become popular. And then to the end, we hope Tensor Tech can make mankind one step closer to become a interplanetary species. This is the dream and goal we have. So thanks for your time today. And if you have any questions, just leave a message for me and I can answer it later on. Thanks for your time. Thank you.